Good afternoon. This is Professor Shannon Gracie. We are working out of the Precalculus Enhanced with Graphing Utilities text by Sullivan and Sullivan today, and we'll be covering one-to-one functions and inverse functions. So you can read our goals there, and let's go ahead and get started with a warm-up. So you may recall that in order for a graph to pass the vertical line test, you can only pass through one point on the graph no matter where you draw a vertical line. So do you see this definitely passes the vertical line test? So for part A, we would say yes. And what about part B? You see it fails in infinitely many spots. It's crossing in two spots in these three examples, right? Crossing through two ordered pairs. So this one is a definite no. Okay, so we'll be talking first about determining whether or not a function is one-to-one. So a function f is one-to-one if no y in the range is the image of more than one x in the domain. A function is not one-to-one if two different elements in the domain correspond to the same element in the range. So let's take a look at this next example. So here we want to determine if the functions given are one-to-one. So part A is in a table, and these are the correspondences. So the first column is the age of 4 males, and that's the domain. And the second column, the range column, is the number of vehicles owned. So here we go. So if you take a look, we have 16 maps to 0, or in other words, 0 is the image of 16. And 2 is the image of 38. Now 1 is the image of 43, and 1 is the image of 60. So this is a function, right? Because each element in the domain maps to exactly one y value, but it is not one-to-one because of these two here. 43 maps to 1, as does 60. So we would say not one-to-one. All right, next up, we have a set of ordered pairs. So here, if you take a look at these ordered pairs, let's look at the input values. None of the input values repeat, and none of the range values repeat. So therefore, this is definitely going to be a one-to-one function. Another way you can do this is you can do sort of a chart where you have domain and range, right? And actually, let's just list the values without repeating. So domain and range. So our domain values in ascending order are -6, -1, 0, and 4. And our range values in ascending order are -1, 1, 3, and 8. So -6 maps to 1, -1 maps to 3, 0 maps to -1, and 4 maps to 8. So do you see that each of the x values goes to its own y value, and they don't go to the same y value. So this function is one-to-one. Okay, So, definition, official definition of a one-to-one function. A function is one-to-one if any, sorry, there's a typo there, if any two different inputs in the domain correspond to two different outputs in the range. So that is, if x1 and x2 are two different inputs of the function f, then f is one-to-one if f at x1 is not equal to f at x2. Okay, so the horizontal line test. If every horizontal line intersects the graph of f in, at most, one point, then f is one-to-one. So here we go. Let's take a look at this one. Now we're doing the horizontal line test, and do you see, if you look here, it passes through 3 points. So this one fails. And then this one is working out just fine. And this one does too. It looks like it's getting horizontal here, but it's not. So you're fine on this one. So it looks to me like B and C. We doing okay? All right, awesome. Okay, here we go, a theorem. A function that is increasing on an interval I is a one-to-one function on I. So if you take a look at this line here, do you see as we move from left to right, it's increasing, and it is one-to-one. Now, if you look here on this other graph, this really either side, as you move from left to right, the graph is going down. And so it is decreasing. So the same will hold true. Okay, so inverse function of f. Suppose that f is a one-to-one function. Then, to each x in the domain of f, there is exactly one y in the range. And that's true because f is a function. And to each y in the range of f, there is exactly one x in the domain. And that is because f is one-to-one. The correspondence from the range of f back to the domain of f is called the inverse function of f. So this symbol here, which is read f inverse, is used to denote the inverse of f. So it does not mean f to the negative 1. It means f inverse. Okay, so here we go. Find the inverse of each one-to-one function. And then we're supposed to state the domain and range of each inverse function. So if you feel confident, go ahead and do it on your own. Otherwise, I shall be working them right now. So if we're switching all of the values, then our new domain will be good. The monthly cost of life insurance. And the new range, or the range of the inverse, will be age. So 709 corresponds to 30. 840 corresponds to the age of 40, and 1129 corresponds to the age of 45. So if we list the domain, remember we're doing the domain of the inverse. So the domain of the inverse will be 709, 840, and 1129. And the range of the inverse is 30, 40, and 45. I'm going to write here just so you don't get confused. Domain of inverse. Range of inverse. Okay, so next up we've got a set of ordered pairs, all right? So the domain, the inverse function will be the set. You just switch your x and y values. So 1, -6, 3, -1, -1, 0, and then 8, 4. So the domain of the inverse is the set 1, 3, -1, and 8. And the range of the inverse is -6, -1, 0, and 4. How's it going? You feel good? Great. Okay, 2 facts about a one-to-one function f and its inverse f inverse. Domain of f equals the range of f inverse. The range of f is the domain of f inverse. So it switches. Okay, so second fact. If you evaluate f at f inverse at x, so you're composing f with f inverse, you get x, where x is in the domain of f inverse. And if you evaluate if you compose f inverse with f at x, you'll get x, where x is in the domain of f. So, coming to our next example, we're supposed to show that each function is the inverse of the other. So let's check it out. Step 1, we basically have to show, verify that f evaluated at g at x, is that equal to x? So f would be evaluated at x plus 8 over 3, because that's what g at x is. And we want to know, is that equal to x? Well, f is 3 times x minus 8, so we'll replace the x with x plus 8 over 3. And we want to know, is that equal to x? Well, do you see the 3's divide out? X plus 8 minus 8 is indeed x, so x equals x. So that one checks out. Next up is g evaluated at f at x. Is that equal to x? Well, f at x is 3x minus 8, and we're going to plug that, we're going to replace the x in the function for g with 3x minus 8. and see if we get x. So 3x minus 8 plus 8 all over 3, is that equal to x? Well, we'll get 3x minus 8 plus 8 is 3x divided by 3. Is that equal to x? Coming up here, x equals x. So we have verified that the functions are inverses of each other. Okay, graphs of a function and its inverse function. There is a relationship between the graph of a one-to-one function f and its inverse, f inverse. Because inverse functions have ordered pairs with the coordinates reversed, if the point AB is on the graph of f, the point BA is on the graph of f inverse. The points AB and BA are symmetric with respect to the line. Good. Y equals x. Therefore, the graph of f inverse is a reflection of the graph of f about the line y equals x. All right, so here's a theorem. The graph of a one-to-one function f and the graph of its inverse, f inverse, are symmetric with respect to the line y equals x. So let's check this out. So example 5, use the graph of f below to draw the graph of its inverse function. So let's take a look at some of the points that are on f. So I see an ordered pair here. You see this one looks to be 2, 8. This guy seems to be 1, 1. Right here I'm seeing 0, 0. You can probably guess what graph this is. And then down here we have -2, -8. So, points on the graph of f inverse. Well, if 2, 8 is on the graph of f, 8, 2 is on the graph of f inverse. Now, when you switch these, you'll get the same. And the next two, so easy it's hard, right? And the last one, we'll flip them and get the point -8, -2. So, if you take a look, this is the line they're supposed to reflect across, that the graph reflects across. And you can see the ordered pairs that we've gotten so far are following that. So, when we do our graph, we'll have something like that. We good? All right, awesome. So this is the graph of f inverse. And this here was the graph of f. Okay, so steps for finding the inverse of a function defined by an equation. So replace f of x with y in the equation for f. Interchange the x's and y's. Solve for y. If this equation does not define y as a function of x, the function f does not have an inverse function, and you're done. If this equation does define y as a function of x, the function f does have an inverse function, and you go to step 4. So if it does have an inverse function, you replace y in step 3 with f inverse at x. We can verify our result by showing that f composed with f inverse at x equals 2x, and f inverse composed with f at x equals x. Okay, so let's find an equation for f inverse at x for these two examples. My kitty is helping us today with the math. I don't know if you can hear her meowing. All right, so let's put our steps in the middle. Step 1 was replace y with, or replace f at x with y. Step 2 was switch x and y. Step 3, solve for y. And step 4, if you can, was replace y with f at x, or f inverse at x. Okay? So, step 1, y equals 4x. Step 2, switch them. So x is 4y. Step 3, solve for y. So you have x equals 4y. Divide both sides by 4. We'll end up getting, if we write y on the left, we'll get y equals x over 4. And that fourth step, replace y with f inverse at x equals x over 4. And you're done. Now the next one, is a wee bit harder. So the step 1, replace f at x with y. And then switch the x's and y's. So, solving for y. So you're going to have to multiply both sides of the equation by y plus 1. And you'll get y plus 1 times x is equal to 2y minus 3. So then we'll get xy plus x is equal to 2y minus 3. We need to get the y's on the same side of the equation so we can factor out a y. So let's see. If I have, basically, I'm going to subtract xy from both sides. And I'm going to add 3. So then we'll have 3 plus x is equal to 2y minus xy. 3 plus x, actually, just pretty that up. We'll write it as x plus 3. Factoring out a y, we'll get 2 minus x remaining. Dividing both sides by 2 minus x, we get this. So, step 4, replacing y with f inverse at x, we get x plus 3 divided by 2 minus x. And you're done. All right. So now our application. So the function t at g equals 1700 plus 15 hundredths times quantity g minus 17,000 represents the 2011 federal income tax T in dollars due for a married filing jointly filer whose modified adjusted gross income is G dollars, where 17,000 is less than or equal to G is less than or equal to 69,000. So what's the domain of the function T? So easy it's hard, right? They gave it to you right here. So it's 17,000 all the way to 69,000. I'm just putting it in interval notation. Given that the tax due T is an increasing linear function of modified adjusted gross income G, find the range of the function T. So that tells us if we plug in 17,000 to the function, that'll get us our initial range value, and then our ending range value will be found by evaluating T at 69,000. So let's do it. So T evaluated at 17,000 is, let's get our calculator out. So we'll have 1,700 plus 0.15 times the quantity, 17,000 minus 17,000. Oops. Enter. So you get 1,700 and T evaluated at the right endpoint, which is 69,000, will be, so I'm just going to hit second entry or second enter. And then in for this one here, we're going to put 69,000. And we get 9,500. So the range is going to be from 1,700 to 9,500. All right, so now what if we wanted to find the adjusted gross income G as a function of the tax T, right? So we're basically going to isolate a different variable here. And you can do this because it's linear. So let's go from this. So let's write, instead of T at G, let's write it as T in equation notation, equals 1,700 plus 0.15 times G minus 17,000. Now, what we want to do is we want to isolate G instead of T. So to do this, we could subtract 1,700 from both sides, and we'll get T minus 1,700 is 0.15 times G minus 17,000. And then if we divide both sides by 0.15, we'll get T minus 1,700 divided by 0.15 equals G minus 17,000, because these will divide out. And then coming over here, adding 17,000 to both sides, we will get T minus 1,700 divided by 0.15 plus 17,000 equals G. So writing G in function notation, we'll have G at t equals t minus 1700 divided by 0.15 plus 17,000. And you're done. All right, so domain and range. So the domain, it's going to be real easy. So the domain is going to be, you got it, the range of the original function, 1700 to 9500. And the range is going to be, good, the domain of the original function, which was from 17,000 to 69,000. Okay? And that wraps it up for this lesson. So have a fabulous day. Bye.